Ivan. So thanks for this introduction. And so Peter has spoiled some of my slides already, but you'll see what it's about. So I'm not used to give technical talks in Russian, so this is going to be in English. I hope you will survive, but we can take questions in Russian later on. Okay. Right. So this is the scene which was already spoiled, and so the talk is going to be about on the intersection of vision, NLP, and robotics. And to put yourself in a context, so let's see this time-lapse video where there is a task of cleaning a house. And so apparently this task is not so difficult. Even kids can do it, although not my kids. My kids usually do it in reverse order, and I've already given a hope. And so these kids are really amazing. They do, they really know the mom is coming in 10 minutes, apparently. So this is a vision task. I mean, partly this is a robotics task, but it's obviously also a computer vision task, because to deal with the scene, you need to understand what it is, because the mass is always a different one. So vision was really successful in the last 10 years. So let's see what vision can help us. So vision, we can detect objects, great. So we can even detect actions, recognize actions of people, or do human poses. Question is, so all this great progress in computer vision, how much does it really help if we want to understand the scene for the task of cleaning it, right? And because I've given away the hope that my kids will do it, so I really need the help of this guy. So how can we explain the robot how should it deal with the scene, to clean, to cook, to lots of things which we would like to do it at home, right? So this is again, vision task, NLP, we will see it in a moment, where NLP comes in, and of course robotics. So we want this all together and to solve the task. All right, so let's move on. Okay, so how, and by the way, so currently there are no systems which can solve these tasks at the moment. So it's really a challenge, despite all the work in robotics and vision for many years. So it's apparently very hard task still for robots. So it's when the task is hard, it's normally good to try to decompose it a bit. So, for example, to separate into two sub-problems. And the two sub-problems typically people address are navigation and manipulation. Okay, they are not really independent. Navigation will depend on manipulation, vice versa. But it's a good first step to just address them separately. And why, by the way, this division? So navigation is what you need for navigation. You need vision, you need perception. But in navigation, the contacts are simple. So you can assume that if I say go from A to B, if the robot is wheeled, or maybe it's a dog, robot dog, which already been quite pre-trained well to just move around. So that's not a hard part. Okay. So for manipulation now is a different story, because now you need to touch the objects, or you need to interact with many. Like if you're making a salad, you cannot imagine of making a 3D model of a salad. So although there are simulators and there are many ways to address it, so contacts is a really hard problem, because really we don't really know how to simulate contacts or physics in good enough for making the robots. And of course we can do experiments on real robots, but then without simulators, but this is even harder because the number of examples you get this way is very limited. All right, so this talk is going to be about some of our work, which we've recently done in both domains, in navigation and manipulation, and just first going to talk about a few of them for navigation, and then the second part is going to be about manipulation. All right, so most of it was done by Pierre Rouy and Shiji Chen, who are our postdoc and PhD students. So let's look at recent domain of vision language navigation, so it's called. We didn't come up with it. The data sets already exist. So what is it about? You're given an agent. An agent is placed somewhere in a room, in a house, which has not observed before. And actually, the agent is not given even a map, so it's just put in a house. Okay? And it needs now to understand and follow the instructions here on the left, sorry. And the only observations it perceives are these panoramic images. So we assume that the agent knows what is around with the camera input. So it's a kind of real problem if you wonder robot which navigates in your house or in any new house or maybe here in the corridor. So in you give instructions, it needs to understand both instructions and the world through vision. And it, of course, needs to not just understand what is understanding, it needs to align the image observations to the text observations and not to forget what is seen before. Again, so the house is there, but it's not given to the robot. So the only observations are given are these images, and the robot can make an actions. Once it has a set of here, it has a discrete set of actions, move left, right, move forward. Right? So it's given the language, natural language instructions, it needs to choose the correct actions, move forward, and hopefully arrive to the goal. Right? So that's how it works. And then, okay, imagine metrics. So if it arrives to the goal or not, so you get the success. Again, so importantly here, actually, we can do offline experiments. We don't need a real simulator because we cannot just assume that if we say to robot, move forward, of course, there might be collision, but this is also easy to simulate without any physics simulator. So here really we are abstracting it from physics, anything of physics, and just dealing pure with vision, language, and actions which are predefined. So good thing is that you can really do experiments here offline. You don't need to run a robot. You don't need to run a simulator. Right? The challenges are that, of course, the more you move around, the more of these observations you have. It's easy to get lost, because if you're not trying to build a map or any memory, so the robot maybe can go in circles forever. So this is one of the challenges which we try to address in this work, is how to build the history of observations and actions. Right? And so here's the architecture, which is nicely put it all together. So it's transformer. So the thing this work was from 2 years ago, so it was probably the first transformer architecture for this type of problem. So transformers are great because they solve tasks in NLP in vision, but they're also great because they can aggregate multiple types of inputs. Okay, so language, images, and now even actions of the robot, so everything becomes tokens, and then you put it in transformer, and you train, and you get results. Although there's a caveat here so our goal is now to represent the history of observations using transformer. So one way to represent history is just to put all the previous observations inside and train. Transformers are complex, they have quadratic complexity. So if the robot is moving more and more, it will accumulate observations. So this is going to be a problem for the memory. So there is a trick here which we apply, is a hierarchical transformer, which instead of so usually these images of panoramas, they are divided into views, and then so we encode the views, but then we have a panoramic transformer which summarizes all these views into one vector and puts it into a temporal model. All right, let's see results. There are quite a bit of benchmarks already in this domain, like air-to-air RVD. And this transformer, all the ablations, it's not just transformer there, but really the history is important. Actually, we'll see it in the next slide. So the method was performing better than all other methods by the time of publication, right, on all the benchmarks. And especially performing well on air-to-air back. So this is like twice longer than room to room, or the first column. So it seems that history is especially helping if the longer the path of the robot needs to do to get to the target, the more performance we get, the more improvement we get because of the history. And history, here's the ablation for the history is really helpful. So the first is just recurrent unit network, which was been used before quite a lot. So you're probably aware of recurrent neural networks where the state of previous observation is summarized by one vector. And this is not as good as representing the history in explicit way by all the observations. Now, of course, there are limitations. So one is that when we model the history is a sequence of previous observations. And sequence is actually if the robot is moving around, so it will be a sequence, but it will not realize that it's moving around. So it's good idea to maybe to model it more as a graph, and that's what this duet extension of our work is doing. So it knows now that, so if it gets stuck, for example, here, right? So it went here and then got stuck here. So in previous work, so we could just, if we had three possibilities, go back here or here. Now, remembering the whole graph, we can actually jump from any position to the network can choose which node to go, okay, and then it will traverse the graph and get there. And so that was submission also to a challenge. So you got the first prize. Also was 2 years ago. Right? Let's see on example how it really what is the agent is observing. So here's one of the houses, actually a museum probably, and so it's given a step-by-step instruction. So exit the roped of hall, follow the red carpet. Okay, and the task is not so obvious here because even for us people, because here if you are standing here, the red carpet goes both ways. So actually the robot cannot really know from this description. The agent doesn't know where to go. So it needs to go, choose an action and to follow red carpet, which it's doing. And then eventually, so it gets stuck because the instructions say turn right, but there is no turn right. So it needs to do something else if it understands instructions. So the network here automatically decides that it needs to go back, and then it chooses the other path and eventually moves to the target. So again, the important thing is that there is no, this parsing of the text, alignment of the text to instructions which are visualized here, they're done by us, right? So it's not by the network. So network is interpreting all the text. It needs to align internally, of course. It needs to align the text, correct part of the text to the current observation, to the current scene, but it's all done implicitly. So it's not. There is no explicit parsing of the text, and then now we are doing this action, that action. So it's all done automatically and trained end to end. All right. So one more work also on navigation, which is related to what I just described. So I've talked about HUMT. HUMT is modeling the history as a sequence of observations. Then Duet was modeling the observation as a graph. So graph is great, but it still doesn't have the spatial structure. So it has it has connectivity, but it doesn't have the spatial structure in a sense that I know that if I'm going there, this room is to the left and so on. So this model is also it tries to encode the house, right? Not in a geometric sense, but in a way it is a geometric representation, but it is implicit representation. Okay, so how it works? So it's a memory unit. Actually, if we reduce it just to 1 by 1 vector, it becomes just a recurrent neural network or recurrent transformer, which people have used before. Now, so what we are encoding here, we are encoding the spatial structure. So when the robot is first first location, so we put it in the middle of this cube, but then when the robot moves around, we augment this memory with the location of the robot and then update the memory in a recurrent way. So we think of it as a map. It's a spatial map because it has a spatial coordinates, and it's also a memory. So the more robot moves around, so we update the map, and the memory is then when the robot, say, moves back to a position where it has been before, so it can access to this memory and retrieve the useful features. All right. So again, the architecture is transformer, so it's all trained end-to-end, and here are some results. So you can see also the instructions are now a bit different. It's not saying like you have to follow the corridor, move right, move left. So it just the instructions received is just chair or bed, and it needs to go around and find these objects in the house. Okay? And it's important that it memorizes some parts of the environment where it has been before, so it has a clue. Actually, here you see the data which is used for training. I mean, these are test sequences, but this is exactly the data which is used for training. So there are some houses which are filmed in 3D and reconstructed in 3D, and that's how it's easier to construct a training setup. Right. So the model, by the way, okay, it was probably in the previous slide. So it's trained with the behavior cloning. If you're familiar with some reinforcement, like policy learning and robotics, so it's a behavior cloning and reinforcement learning. So behavior cloning assumes that some people already, it's kind of supervised learning where the algorithm receives the trajectories, the ground truth trajectories for. All right, I hope this will move on. Okay. And now, so you can also apply it to real robots. Okay, so same policy which was trained in simulation, now fine-tune a bit on a real robot, and so it can find the plant, it can find the sink, it can find the sofa. Right, so still a bit far away from cleaning the house, but these are the first steps. All right, so if you have any questions for navigation, I guess questions will come later. So let's talk about manipulation, which is the next topic. And as I said, so manipulation is a harder task because you need to model much more in terms of actions and physics. But the tasks are really, there are plenty of tasks. Like if you buy IKEA furniture, you need to someone needs to assemble it. So if you want to cook your favorite dish, maybe you don't have time, or you want to press a button in your office and it will be done when you get home, or arranging and cleaning and lots of stuff, which are, by the way, so currently, although robots are great in doing vehicles like cars, well, otherwise cars would be much more expensive. So now when it comes to simple tasks like home, or actually anything which involves moving around and an unstructured environment, the robots are currently quite useless and hopeless. So we need to change this. So now, let's see in the manipulation. So what are the challenges? So first, there are really lots and lots of different tasks. There's a precision. Some tasks need precision. If you need to open a bottle, so you need to really put the gripper on your bottle. So there is your observations don't reveal all the physical state of the world. And yes, and the world is complex and unpredictable. So we are not planning to reconstruct scenes like this in 3D, like with all the material properties and so on. So these are challenges. Now, how can we deal with all of them? So first, like how to deal with many tasks. So imagine that you trained one policy which is guided by language. So if you can just talk to your agent to define a task by language, and the robot or agent will do it. So you can actually, language is a great interface between machines and humans, of course. So now the precision is important and can be actually handled quite well if we don't observe the world from one camera, but from many cameras. Like we have 2 eyes, this already helps. But if you can have an agent which can have more views, that really helps precision, and it's very easy to integrate. The current observation is sufficient. You can go back to history, as we did for navigation, and here is the so we're going to use depth. We are not going to reconstruct the world, but we are going to use depth, which you'll see will help. And transformer is our helper here again, so it can take all these kinds of inputs, language and multiple views, depth, whatever you put it, and then let's see how we integrated all of it. So of course we want to integrate it in different ways. So this is one, and so first, interesting observation. So that was this work was about it was corralled last year. It was no GPT probably by that time. So, but the bird. So we build on language models which are pre-trained, right? So that's obviously useful because if we're going to train policy from scratch, to understand language, we know we need lots and lots of data, which will not be available for our tasks. So it's good idea to pre-train it for some other tasks, but now which task? And so you can just take a language model like BERT or GPT, which is just trained for language only. So what we found that this is actually not a great idea because language-only pre-trained models, they know about language, but they don't know about vision. They don't know much about the world around. So CLIP, which is trained just by current standards, not the biggest one, but still it's trained for vision and for language together, and actually it works better because, for example, it knows about colors. Okay, so and then multi-view, easy. You just put different cameras and different places and put it all into transformer. Although how you construct what is the transformer? So transformer needs some tokens. So how you tokenize your input is important. So we put it through UNet, get some observations for the scene with spatial dimension, filter dimensions. Now, if you building tokens could be done in different ways, like to put it into transformer. If you channel this cube of data of your features and define tokens as channels, this is not going to be great, as we'll see. So patch tokens are much better. Okay, some more details like cross transformer is cross attention is better than self attention. We'll see, and behavior cloning. This is the way how it's trained. Okay, so what's the task? There's a benchmark. There are a few benchmarks. Now this is really simulator, so you need to simulate physics. Okay, so in previous, when we talked about navigation, we didn't have to have physics simulator. Here it's really a physics simulator with gravity, with friction, with everything. So which you have to run during training and during testing now, which takes time. So these are more complex stuff. So so these tasks are okay. They're just defined, and some of them they have also fine-grained variation. And fine-grained variation, this is really where we can test the language. So we can, for example, separate the task for training and testing, where training is going to have some variations and testing will have other variations which have not been seen during training. Okay, so a few results. The first, so if we use multi-view, this is really helpful. Just this is really easy. You put many cameras in the scene, and the more cameras you put, the better performance you get. Okay, probably saturates. We didn't try more than 3, but it was clearly a win if using 3 cameras instead of 1. History helping, about 4%. Patch tokens and cross attention versus self attention is also useful. And overall 15%, which is quite a lot. All right. And also important is that now for this task, fine-grained task of, for example, pressing buttons, where by language we say that the sequence of colors in training and testing is different. So we get some drop of performance for unseen variations, which is normal, but still works. And then, okay, some more drop of performance if our language is more sophisticated and natural, which we define the comments, but it still works. And now, so last work I'm going to present, it's follow-up from what I just described. So the task is the same. We have many tasks, complex tasks, which I described by language. Now, the difference is the representation. So what we found, and there are a few people who follow this, that how do you represent the 3D world? So I told before that it's not very good idea probably to reconstruct everything, because if you have unknown, like previously unseen objects, reconstructing them is going to be hard. Now, instead of depth map, we can use the 3D point cloud. And 3D point cloud seems to be a great representation for robotics, which can be processed by networks like PointNet and other developed network after it. So now it's not just a point cloud, it's also point cloud with color. So we observe the scene from multiple views. We have depth map. And so with the depth maps and RGB images, they give us point cloud and 3D world, and we can also project the color from RGB images to these points. So this is really helpful. And now the architecture is like this. So we have a point cloud as input. We put it through point next encoder. We have a transform architecture, and then at the end, so we get again a point cloud, but now the point cloud also has a location of the action or of the manipulator where it should go next. So if the task here is, I don't know, to grab the red cup, for example, so the network will predict the point cloud, and if you take the mean of this point cloud, so it will be exactly the location where the robot should move next. All right, and so these are some results. Colors are really, really helpful. So just going from point cloud to colored point clouds, it gives about 20% of improvement. Again, multiple cameras is really, really helpful, and this is really easy. Just putting more cameras, and okay, some more details. Maybe I'll skip. Right. So here, okay, state of the art. So this work was presented a few weeks ago at Coral, and so it outperforms other methods, and yeah, that's how these are some just examples of the tasks. And now, so this network has been trained in simulation, but now we can transfer it to real robots with a few. So we need some few real observations from real world. Otherwise, if you just train in simulation, try to deploy it on the real robot, it doesn't work very well. All right, but now it's actually, yeah, you can manipulate objects. You can just define tasks by language, and still kind of simple task. The robot is static, but these are the steps towards something bigger. Right, so that was the summary. I hope it was useful. So I want to finish with a few observations. And first, just saying that, okay, computer vision language obviously has done lots and lots of progress. Robotics is behind, but I think it's very important that now it's a good moment for the synergy, so combining all of it. We know that language is helping vision a lot. Vision maybe helps language a little bit. So all of it the language and vision will help robotics. But also, I believe that robotics has a big potential to help vision. And so here are a few examples to finish. So what I'm most interested now is the so-called embodied vision. What is embodied vision is computer vision, but which cares about physics. And so here's an example which shows that GPT-4V, which is supposed to understand vision, so it tries to understand physics, but not is quite there yet. So if you just give it an image like that and ask what will happen if people will turn and walk left, okay? So this is not solving the task, and which is obvious for us. So here's another one, a bit more sophisticated. So, well, if you try to pull, well, I understand if your kid trying to pull the tablecloth from the table, unless the person is really skilled, like I guess this person is. So the things may go wrong, but okay, the GPT is not understanding this at all. Right. So I think there are lots and lots of interesting problems still in computer vision, really in research, which is on the intersection of robotics, computer vision, and language. And that's what my new lab is trying to do. So where I am now, so I'm in MBZUAI. It's the first, advertised as the first University of Artificial Intelligence. It's in Abu Dhabi in Emirates. It's really, they're really trying to put the high standards. So it's currently even after, it's just new university, just 3 years old, but it's already top 20 in these 3 fields, in machine learning, computer vision, NLP. So I'm there since 3 months. I like it, and I'm building a new lab, which is focused on embodied and language-aware visual models. So there are positions available. So if you're interested, or if your students are interested, so yeah, you're welcome to apply. So this is it for me. Thank you for listening.
Иван, спасибо тебе большое за такой интереснейший доклад. А мы потихоньку переходим к вопросам. Напоминаем также зрителям, те, которые находятся в офлайне, вы можете задавать свои вопросы в чат-боте. Для зрителей онлайн вам доступен чат. Ну и первый такой вопрос, интересный, наверное, касательно всей вот этой истории. Учитываете ли вы как-то сейчас, может быть, как-то уже в будущем, физические свойства объектов?
Естественно, это важно. Потому что все симуляторы, которые сейчас есть, им нужно, то есть они знают вес, они знают friction параметры, да. Но проблема в том, что симуляторы не очень хорошо справляются пока с задачей. Хорошо. Они хорошо справляются, может быть, для игр, то есть это выглядит правильно, как бы кажется правильным, но когда дело доходит до прямо вот, чтобы повторить реальность, там есть проблемы.
Хорошо. Вопрос от слушателя. Какими, назовем так, филдами оперирует PointNet? Это какой-то унифицированный интерфейс или специализированный интерфейс для манипулятора, или нужно ретранслировать в каждый манипулятор в свои инструкции?
Хороший вопрос. Значит, PointNet, на самом деле, это сеть, которая была придумана не для робототехники. Изначально это сеть, которая может просто сегментировать, например, 3D point cloud на разные объекты и так далее. Вот, то есть мы ее просто взяли, применили для роботов, для агентов, и она работает. Что интересно, у нас как раз новая статья, которая подано, да, еще не принято. Вот, что если притренировать PointNet на различных задачах, то как робототехники, так и не робототехники, то становится тоже лучше.
Ну а вообще, возможно ли end-to-end решение, чтобы мы сразу получали набор транзакций, набор команд?
Это end-to-end решение. Да.
Ну вот, это end-to-end
да,
решение.
Да. Все сети, которые я показывал, это end-to-end.
Супер. Есть ли у тебя вопросы?
Ну, такой, наверное, вопрос больше про будущее. Подскажи, пожалуйста, вот как ты думаешь, насколько скоро, да, мы можем увидеть уже какие-то продакшн решения, которые мы можем, например, повсеместно зайти, купить в магазин и использовать уже в том числе в своих каких-то домашних делах?
То есть что-то большее, чем просто робот-пылесос, который еще может
Хочется
сделать...
что-то большего, да.
Да. Ну, пока сложно предвидеть все, что будет. Что случилось за последний год-два с генеративной AI, никто не предполагал. У меня более консервативные в этом плане. То есть хотел бы, чтобы, конечно, у нас все появилось уже через 2 года, но на самом деле, думаю, еще рано пока что. Думаю, что 5 лет это займет. Мы видим тоже с беспилотниками, с машинами. Тоже они не так быстро входят в наш мир, как некоторые думали несколько лет назад.
Осталось, чтобы манипуляция была «отвези меня домой» и чтобы не укачала. Еще один вопрос. За счет чего модели, которые обучались на задачах манипуляции, могут превзойти фундаментальные модели, которые не сталкивались с реальным миром?
Насколько модели, которые обучались на манипуляции, могут превзойти модели?
На задачах манипуляции могут превзойти фундаментальные модели, которые...
Понятно. Ну, наверное, здесь нету или. То есть есть комбинация. Фундаментальные модели, они, очевидно, будут полезны. Но на данный момент они с физикой справляются плохо. Поэтому точно нужно какое-то их обучение. Естественно, цель — это получить фундаментальные модели, которые понимают и зрение, и физику, и language, и все. Вот здесь пока что горлышко бутылки — это данные. Что у нас много картинок, много текстов, данных именно от роботов или от хороших симуляторов у нас очень мало.
А какие есть вообще, я не знаю, топ-3 прям симуляторы, где можно... Возможно, они создавались не для этого, но их адаптировали.
Есть стандартные симуляторы для игр. Еще раз, игры, они выглядят хорошо, но на самом деле очень плохо.
Физикой.
С физикой у них все очень плохо. Да. Если можно обучить модель, которая будет в симуляторе работать прекрасно, но с реальным миром она ничего не будет иметь. Но так есть физические симуляторы MBZUAI, как один из самых таких неплохих. Они, тем не менее, они плохие. И еще, что проблематично, что они не дифференцируемые. Это значит, что end-to-end решение с ними не получится.
Наверное, еще вопрос, пока есть время. Ты рассказал про PhD Opportunity. Вопрос. Кто идеальный кандидат? Кажется, что совместить и CV, и NLP, ну ладно, это еще возможно, да, но еще и физику, роботикс, это все. Кто по выходу наилучший перформер, кто? Это человек с физическим образованием, который перешагивает, либо наоборот, ML-щики, которые окунаются в физику.
Ну, люди должны что-то понимать уже в нейросетях. Это базовое, да. Vision, мне, чисто для меня, потому что я занимался Vision последние 25 лет, поэтому это будет ближе. Но на самом деле я не вижу в этом большой проблемы, потому что, как уже сказал, все сводится в один трансформер, на самом деле. И то есть, если люди занимались, то есть хорошо иметь, конечно, какой-то бэкграунд, может быть, в механике. То есть можно заниматься всем этим со стороны Vision, больше со стороны робототехники или больше со стороны... То есть здесь разные подходы есть. Я думаю, что главное — это иметь желание и вдохновление заниматься этой
То есть
проблемой.
Нет какого-то оптимального состояния, это всегда нужны все. По-хорошему. Настя, у тебя еще вопросы есть? Или?
Я бы задала еще один вопрос. Помимо физики, какие еще сейчас выделяете, возможно, какие-то проблемы, которые бы хотелось решить, чтобы в дальнейшем ускорить процесс, в том числе разработки подобных решений?
Помимо физики?
Да.
Была 3 моих, да, то, что это физика, это NLP и Vision. Вот. На Coral 23, которая прошла несколько недель назад, у них прямо была сессия, называлась NLP. Да, то есть это конференция для робототехники, Robot Learning. Вот, но у них прямо была целая секция по NLP, где там люди брали просто GPT и как-то его использовали для того, чтобы он давал, то есть переводил, по сути, то есть, наши желания, сформулированные языком в инструкции для роботов. Да? То есть как вместо питон-кода, да, какие-то инструкции для роботов. Это кажется очень перспективно. Пока что посмотрим, куда это пойдет.
Супер. Наверное, на вопросы все. У нас есть стандартный вопрос проявления. Что для тебя было явлением последнего года или чуть больше, чуть меньше, если вот одним словом попытаться или фразой?
Генеративный AI и новые методы для трехмерных визуализаций, как типа Gaussian splitting, и которые, кажется, побеждают nerves, и кажется, за этим большое будущее.
Супер. Тогда ждем на следующей конференции с рассказом и о них. Спасибо большое.
Спасибо.
Спасибо.